In this video, I'd like to talk about some synthesis strategies based on the new reactions that we've learned this chapter. As we always do with synthesis problems, there are two important questions to ask. First, is there a change in the carbon skeleton? And then, in particular, we want to know, did the functional group move in addition to changing the carbon skeleton? Because that's going to tell us about the types of new carbon-carbon bond forming reactions that we might use. And then, this is generally the case, but is there a change in the functional group? And in this chapter, we've learned a lot of new functional group transformations. We learned a ton of new reactions. And so really the only way to get good at this part of it is to do practice. Make flashcards. Fill out your reaction journals. And basically you have to learn the reactions if you're going to use them in these synthesis problems. All right, first let's think about the different reactions that we've learned. And I'm not going to go through this whole figure because these are all reactions that we've already learned over the course of this chapter, but this is a figure from the textbook that I thought was kind of useful in organizing our thoughts on the different reactions. And it may be a way to kind of help learn the reactions and kind of keep them all straight. And so the way this figure is organized is from top to bottom. It's organized based on oxidation state. So the higher the compound is in the figure, the higher the oxidation state. The lower it is in the figure, the lower the oxidation state. Now I know carboxylic acids have the same oxidation state as all these other compounds, but since these are all kind of derivatives of the carboxylic acid, they kind of put this in the central position. But we can see, right, there are ways to go from the carboxylic acid to the acid halide. We can go back to the carboxylic acid from the acid halide. Same thing with the acid anhydride, we can go in both directions. For the esters, we can go in both directions. Now for the amides and the nitriles, we can only go in one direction, right? And we see what the different results are of reducing the various compounds and what we'd have to use to stop at the aldehyde versus going all the way to the alcohol, or the amides and the nitriles, they're reduced to the amines. The other way that these compounds are organized, particularly in this row here, is that going from left to right, they're ordered from most reactive to least reactive. And so in general, it's easy to go this way. I can turn the acid halide into almost any of the other derivatives, but it's difficult to go in the other direction. And so this can give us some ideas on syntheses. Right, I can't go directly from carboxylic acids to the amides or the nitriles, but I could go to the acid halide and then over to the amides and then to the nitriles. Right, and if I see that I have an amine group, and I'm starting with a carboxylic acid, right, I kind of go, okay, I'm going to go carboxylic acid, then to the acid halide, or the ester, or the acid anhydride, whichever, then go to the amide, and then I can go to the amino acid. I'm sorry, not the amino acid, just the amine. So it may be worthwhile to, kind of pause the video here, or maybe it's even easier to pull this up in your textbook, but kind of study this figure and kind of help see how all the reactions that we've learned kind of fit together in converting between these different compounds. All right, so we know that one of the most important questions we can ask ourselves when doing the synthesis problems is, did the carbon skeleton change? And if it did, then we need to go to a reaction that we know creates new carbon-carbon bonds. And we've learned a variety of those in this chapter. We can classify those into two different groups. The ones on the left here add a new carbon-carbon bond, but the functional group remains in the same location. The functional group remains on the same carbon that it was to begin with. And in this first example, we learned that a variety of our carboxylic acid derivatives can react with Grignard reagents. That's why they put the Z here, because this could be an acid halide, it could be an acid anhydride, it could be an ester. Now, it can't be a carboxylic acid because carboxylic acids are very acidic, and they would destroy the Grignard reagent, but this could be the acid halide, acid anhydride, or the ester. When we react that carboxylic acid derivative with excess Grignard reagent and then follow it with a water workup, we add two of the R groups. Whatever the R group is from the Grignard reagent, we add two of those to the carbonyl carbon, and the carbonyl is reduced to an alcohol. Now, specifically with acid halides, we learned that we could react that with the Gilman's reagent, which is less powerful than the Grignard reagent. So rather than adding both R groups, it just add one, and we keep the carbonyl group. It doesn't get reduced to the alcohol. And then finally, we also learned that we could react nitriles with Grignard reagents. That would again just add one R group, and we would keep the carbonyl group. The reactions here on the right create new carbon-carbon bonds, but they also move the location of the functional group. And they move the location of the functional group by exactly one carbon. So we know that we can create the nitriles by doing SN2 reactions on alkyl halides. In this case, the functional group is on this carbon atom. When I turn it into the nitrile by reacting it with sodium cyanide, we're adding an additional carbon, but the functional group is no longer on this carbon, it's on the new carbon that I added. And so I can then hydrolyze that nitrile and convert it into a carboxylic acid, which opens up our whole tree of reactions that we've learned this chapter. But again, the functional group is on a different carbon than it started on. We also learned another way to make carboxylic acids is to react this with magnesium to convert it into a Grignard reagent, then react it with carbon dioxide and follow it with an acid workup, and that would again get us to the carboxylic acid, but again, the functional group is not on the carbon that it started on in our substrate. It moved it over one carbon. So both of these reactions add one carbon, and they move the functional group over one position. Now, that last class of reactions where we move the functional group over one carbon, I think is interesting to compare to a reaction that we learned earlier in the semester. So this was on the chapter with ethers and epoxides. This was a similar reaction, but we moved the carbon atom over by two positions, as opposed to the one position for the reactions we saw on the last slide. Right now, the reaction is kind of similar. We start with an alkyl halide, we convert it into a Grignard reagent by reacting it with magnesium. Now, instead of reacting with carbon dioxide, react it with an epoxide. The nucleophile from the Grignard reagent is going to attack here on carbon 1 to open up this ring, and then the alcohol that we're going to end up with is going to be on the second carbon. So you want to be careful of how did the carbon skeleton change, and where did the functional group move to? If it moved over one position, we'd want to go to the reactions from the last slide. If the functional group moved over two positions, then we'd want to consider this reaction with the epoxides instead of the ones that we saw in the last slide. All right, so I think maybe the most helpful thing for synthesis practice is to do some examples together. And so rather than letting this video get too long, I've got 2 examples on this slide, and then I have a separate video that's just 3 more examples of synthesis problems involving reactions from this chapter. So I'm starting with this carboxylic acid, and I want to convert it into an amine. Now, I don't think we've learned any reactions to convert carboxylic acids directly into amines, and when I think about reactions from this chapter that can make amines, I know that I can get there by reducing an amide. Now, so if I can get to an amide, I can get to this final compound. I don't know how to go directly from a carboxylic acid to an amide, but I do know how to convert a carboxylic acid into an acid halide, which I can then convert into an amide, which I can then reduce into the amine. So if we kind of think about working backwards, right, my last step is going to be to convert this compound into the amine, and so I would do that using excess lithium aluminum hydride and water. And so then my trick is to get the carboxylic acid to that amide. So I know I can get to an acid halide by reacting that with SOCl2. And then I know I can get to this compound using aminolysis. And so I'm going to use two equivalents of ammonia, we need the two equivalents because one of them is going to add to our, it's going to replace the chloride in our acid chloride, and the other one is going to be there to reduce the HCl that we produce. And so these three steps should give me the product. Okay, in the last example, the carbon skeleton didn't change. In this case, I think the carbon skeleton did change. I've gone from 1, 2, 3, 4 carbons where the functional group is to 1, 2, 3, 4, 5. Right, and then the position of the functional group has changed. Here, if I start counting from the left, the functional group is on the 1, 2, 3, 4th atom. Now it's on the 1, 2, 3, 4, 5th atom. So I've got to get from this compound to this ester, but I need to add a carbon to this chain. So I know that I can make an ester from a carboxylic acid, and I know that I have some carbon-carbon bond-forming reactions that will allow me to convert an alkyl halide into a carboxylic acid and add a carbon. I can either go through the nitrile route or the Grignard reagent route. So I'm going to pick the nitrile route. So I'll get an SN2 reaction between the cyanide ion, the bromine will leave as a leaving group to give me the nitrile. And now I have my 1, 2, 3, 4, 5 carbon atoms with the functional group. So now I can convert this into a carboxylic acid. I know if I heat that under acidic conditions, that will hydrolyze my nitrile. To give me the carboxylic acid. I can then convert that into the ester a number of ways, but I think the easiest in this case, since I have the carboxylic acid, is to go with Fischer esterification. And so I'll use propanol in acidic conditions, and because this is an equilibrating process, to force that reaction to go to completion in favor of the products, I'm going to use excess propanol, and that should give me the final product.